Now we will look at some of the phenomena that we see waves undergoing in the physical world. Reflection and refraction both occur when a wave is passing through one medium and then it comes up to the boundary of another medium. Whenever we draw this situation, we label what is called the normal to the surface at the point of contact, a perpendicular line coming out of the boundary. As the light comes into the boundary, we call the angle between it and the normal the angle of incidence. When a wave reflects off of a surface, it bounces straight back off of it. This angle between the outbound light ray and the normal we call the angle of reflection, and we find that the angle of incidence is always equal to the angle of reflection. It bounces off at the same angle it came in at. Refraction is when the light travels into the other medium rather than bouncing off at the boundary. And for this discussion, we will consider light traveling from air into a material with a refractive index of n. The refractive index of a material is a measure of how much light slows down when it goes into that material. Glass has a refractive index of 1.3 and water has a refractive index of about 1.5. Let's say it's light going into a glass block. The slowing down of the light when it goes into the glass block causes it to bend towards the normal. We call this angle between the outbound light ray and the normal the angle of refraction. We find that the angle of incidence, the angle of refraction, and the refractive index of the glass are simply linked by this equation, which is a simple version of Snell's law. Now consider the flip situation where the light is in the medium with the high refractive index, like glass, and the other side of the boundary is a low refractive index like air. This time, if the light passed through the boundary, the light would want to bend away from the normal, since the light is actually speeding up as it crosses rather than slowing down. As we increase the angle of incidence, we reach a point where the exiting light that is being bent away from the normal won't even be entering the air at all. At angles of incidence greater than this, the light is reflected rather than passing through the boundary and being refracted. This phenomena is called total internal reflection, and the angle at which this starts occurring is called the critical angle. Optical fibers use this phenomena to pass light waves down wires. Doppler Shift describes the fact that people measure the wavelengths of waves coming off of an object to be different if that object is moving relative to them. To understand this, imagine an object is giving off waves that travel at 10 meters per second, and it's giving off a wavefront every second. In other words, the time period is 1 second. This means that when a wavefront reaches the observer, the next one will be 10 meters away from them, and so they would measure the wavelength of this wave to be 10 meters. If the object is instead moving away from you at a speed of 2 meters per second, let's see what happens. One wavefront leaves the object travelling at 10 meters per second as before, but by the time the next one leaves, the object has travelled 2 meters away. This means that the new wavefront is 12 meters behind the previous one as measured by the stationary observer, and so they measure an increase in the wavelength of the wave as a result of the object moving away from them. Of course, anyone who is on the object or moving at the same speed as the object will not measure this change. It is caused by the relative motion of the object and the observer. With the same thinking, you can easily conclude that if the object was moving towards the observer would measure a decrease in the wavelength of incoming waves.